Welcome to another deep dive. And oh boy, are we in for a fascinating one today. We're diving into the world of category theory.
Oh, this is going to be fun.
Yeah, we're using the Wikipedia article on category theory just to, get everyone up to speed on what it's all about. It's kind of a surprisingly widespread area of math, shows up in a lot of places.
Yeah, it's interesting how category theory is kind of like you're zooming out, right? You step back from looking at individual structures and instead look at the relationships and patterns between them.
That's a great way to put it. Yeah, so instead of getting lost in the specifics of like one mathematical object, we're looking at these larger universal principles that tie everything together, these connecting threads.
Exactly. And the beauty of it is, often these connections reveal a deeper understanding of those individual structures themselves. It's almost like understanding a word not just by its dictionary definition, but by, how it's used in a sentence, the context.
I like that, yeah. Okay, so the Wikipedia article jumps right in. Starts by introducing these like basic building blocks of category theory, objects, and morphisms. Can you unpack those for us a little bit?
Of course. So objects, those just are the things that we're studying, right?
Yeah.
Could be anything really, sets, groups, topological spaces, even logical propositions, you name it.
Gotcha, okay.
Now, morphisms, those are the arrows that connect these objects.
Hmm.
You can think of them as representing relationships, transformations between the objects.
So like if we're thinking about sets, the objects would be the sets and then the morphisms would be functions between them.
Exactly. But here's where things get even more interesting. Morphisms, they don't have to be functions. They can be any kind of relationship that makes sense in the context of that particular category that we're looking at.
So it could be like a comparison or a transformation, a logical implication, really anything that connects these two objects in a meaningful way.
You got it. And that flexibility, that's actually one of the things that makes category theory so powerful.
Yeah.
Because it allows us to abstract away from those very specifics of, individual mathematical structures and instead focus on these underlying relationships that connect them.
Okay, I'm starting to see how this all fits together.
Gotcha.
And so then to like actually visualize those relationships between morphisms, that's where these commutative diagrams come in, right?
Yes, exactly. Commutative diagrams, they're essentially, maps of our categories. We use dots for the objects and arrows for the morphisms. And then the way those arrows connect, that tells us how all the different morphisms relate to one another.
Ah, okay, I see. So if like one morphism takes us from object A to object B, and then another one takes us from B to C, the diagram shows us how those two morphisms combine to create a path from A to C.
Precisely. And the beauty of these diagrams is that they capture the essence of those relationships between the morphisms without, getting bogged down in the details of specific functions or transformations.
Yeah. Right, they give us the big picture, the overall structure. So it sounds like these diagrams really provide a visual language for navigating this whole intricate network of relationships within a category.
That's a great way to think about it. They allow us to see the forest for the trees, you know what I mean?
I do. Now, the Wikipedia article also mentions these things called functors, which seem to take things to an even higher level. These connect entire categories now, right? What are those all about?
Sure. A functor, you can think of it almost like a morphism. But instead of connecting individual objects, it connects entire categories. So it's like a structure-preserving map that takes objects and morphisms from one category and then maps them to objects and morphisms in another category.
So it's not just randomly shuffling things between categories. It's carefully preserving those essential relationships defined by the morphisms.
Exactly. And there's two main types, covariant and contravariant. A covariant functor that preserves the direction of the arrows, and then a contravariant functor reverses them.
Oh, that's interesting. So why would you want to reverse the arrows? It seems like that would completely change the relationships within a category.
It might seem that way, but reversing the arrows sometimes can actually reveal these hidden connections and lead to new insights. It's like, looking in a mirror, it's still you, just flipped.
Okay, I think I see what you mean. So we've got objects and morphisms within categories, and then functors connect and compare different categories. It's like building this giant interconnected network of mathematical structures.
It is. That's a great analogy. And just like we can compare objects using morphisms, category theory actually gives us a way to compare different functors. That's where natural transformations come in.
Oh, so we're going meta now, comparing the things that compare things. I'm intrigued. Tell me more about these natural transformations.
All right, so a natural transformation is kind of like saying, look, these two functors are kind of doing the same thing, but here's how their approaches differ. They basically give us a way to measure how close two functors are to each other.
I see. So if we have like two functors that map categories of shapes, a natural transformation might tell us how one functor prioritizes preserving angles, while the other one focuses more on areas.
That's a great example. And sometimes a natural transformation might even reveal that two functors are actually doing the exact same thing, just disguised in different ways. That's what we call a natural isomorphism.
That sounds like a pretty powerful concept.
It is, yeah. The idea that these seemingly different constructions can be essentially the same. It allows us to translate results between seemingly unrelated areas of math. It's like discovering a hidden tunnel connecting two totally different landscapes.
Okay, so we've established this idea of functors, like they're connecting these different categories, and then natural transformations, giving us a way to compare them. I'm curious, though, what are some concrete examples? Where do these abstract concepts actually give us, practical insights?
Well, one of the most fascinating things about category theory is that it gives us these elegant and universal definitions for things that we think of as really basic mathematical concepts. So for instance, let's think about something as simple as the empty set.
Okay.
Right. Traditionally, you define it as the set with no elements. But category theory, it lets us define the empty set purely in terms of its relationships with other sets.
Oh, interesting. So instead of describing what's in the empty set, we're describing how it interacts with its surroundings.
Exactly. Category theory defines the empty set as the unique set, such that for any other set, there's exactly one function from the empty set to that set. It's like the empty set is the ultimate starting point for any set-to-set journey.
Yeah, that's a very different way of thinking about the empty set. Instead of focusing on its lack of content, we're highlighting its unique role in this network of relationships between sets.
Exactly. And this approach isn't just limited to the empty set. Category theory gives us a way to define all sorts of fundamental concepts like products, coproducts, kernels, quotients, all in terms of their relationships with other objects. These are what we call universal constructions.
Okay, and the Wikipedia article mentions something about limits and colimits. It says these are key to these universal constructions. What exactly are those?
So you can think of limits and colimits kind of like blueprints for constructing these new objects from existing ones. They capture an essential property. Like we're saying, give me an object that relates to these other objects in this very specific way.
Could you give an example, maybe, to make it a little more concrete?
Sure. Let's consider the product of two sets, right? In traditional set theory, we define that as the set of all possible ordered pairs, where the first element is from the first set, the second element is from the second set.
Right.
But in category theory, we define the product of two sets as a limit. We're basically saying, give me an object that has projections onto both of these sets, and any other object with projections onto these sets factors uniquely through this object. So we're capturing that essential property of a product without having to rely on the specifics of the elements or the internal structure.
Okay, so it's like instead of listing out all the elements in that product set, we're defining it by its position, like its role in the network of relationships between sets. Almost like, I don't know, defining a word by its grammatical function rather than its dictionary definition.
That's an excellent analogy.
Yeah.
And this has really profound implications because it lets us define complex mathematical objects in a way that's concise and also universally applicable across different categories.
It sounds like category theory is providing this whole new language for expressing mathematical concepts. And this language, it prioritizes those relationships and connections over internal structure.
That's a great way to put it. And just like languages can have synonyms, right? Category theory has this notion of equivalence of categories.
So two categories can be equivalent even if, on the surface, they look totally different. What would that even mean?
It means that they have essentially the same content, mathematically speaking. It means there's a way to translate back and forth between those objects and morphisms in those two categories without losing any of the important information.
Do you have an example where, two seemingly totally different areas of math turned out to be equivalent through the lens of category theory?
Absolutely. One of the most famous examples is the equivalence between propositional logic and Boolean algebras.
Okay.
On the surface, they seem quite distinct. Propositional logic, that's about statements that can be true or false. Boolean algebra, that's dealing with sets and operations like union and intersection. But category theory shows us that there's this really deep connection between them. We can construct a category where the objects are propositions and the morphisms represent logical implications. And then we can also make a category where the objects are Boolean algebras. The morphisms are structure-preserving maps. Turns out these two categories, they're equivalent.
So the relationships between those propositions and logic, they have a direct correspondence to the set theoretic operations.
Precisely. And this equivalence allows us to translate results between the two. For example, a theorem about logical implications, that can be translated into a theorem about Boolean algebras, and vice versa.
That's incredible, like, again, discovering this hidden tunnel between what we thought were completely separate areas of math.
Exactly. And that's just one example. Category theory has revealed these surprising equivalences between all kinds of areas in math that seem completely different at first glance. And that leads to all these new insights and deeper understanding of the interconnectedness of all this mathematical knowledge.
This deep dive is already one of the most fascinating ones we've done, that's for sure. The Wikipedia article even hints at some even more advanced concepts, like adjoint functors, and even like higher dimensional categories.
Yeah.
Before we get into those, I think I need a minute to process everything we've learned already.
Yeah, I agree. This is pretty deep stuff. It's important to pause every now and then and just take in, appreciate the vastness of it all.
All right, I think I've, kind of caught my breath after that mind-bending exploration of equivalence. I feel like we've been through a lot.
Yeah, no kidding.
So where do we even go from here? The Wikipedia article, it mentions some even more abstract concepts like adjoint functors and even higher dimensional categories. Like, whoa.
Those are definitely the more advanced and mind-boggling aspects of category theory.
Yeah.
But I think before we venture into those territories, it might be a good idea to just kind of recap, the key insights we've talked about so far.
Yeah, that sounds good. I'm still trying to fully wrap my head around everything.
Yeah, well, the core idea here with category theory is that we shift our focus, right? We're moving away from the internal structure of mathematical objects, and we're looking more at the relationships between them.
Right, right. So instead of asking, what is this object made of?
Yeah.
We're asking, how does this object connect to other objects?
Exactly. And we've learned about some of the key tools that category theory gives us to explore those connections. Objects and morphisms, those are like the building blocks of categories,
Yeah.
right? Then you've got functors, connecting whole categories, preserving the structure. And then natural transformations, which let us compare different functors and uncover these sometimes really surprising equivalences.
It's like we've been given a new set of lenses, to view this mathematical world, and they're showing us all these hidden connections, patterns that we wouldn't have seen otherwise.
That's a great way to put it. And as we go deeper into category theory, those lenses get, even more powerful, allowing us to see these connections that span huge mathematical landscapes.
Okay, so what about those more advanced things you mentioned, the adjoint functors? What kind of insights do those give us?
Adjoint functors, they're a little bit tricky to explain concisely, but they essentially capture this kind of duality between different categories. They let us translate concepts and constructions from one category to another while still preserving certain properties.
Okay.
Yeah.
Can you give an example, maybe,
Right.
where this duality would be useful?
Sure. One classic example is the relationship between free groups and forgetful functors.
Right.
So a free group, that's a group that's generated by a set of elements, right? And a forgetful functor, that's a functor that kind of forgets some of the structure of a category.
Okay.
So in this case, the forgetful functor, it takes a group and it maps it to its underlying set. So it's basically forgetting the group operation.
Ah, I see.
And then the adjoint functor to this forgetful functor, it takes a set and maps it to the free group that's generated by that set. So this duality between free groups and forgetful functors, it has some deep implications in algebra and topology.
Wow, that's fascinating. It sounds like adjoint functors are this powerful bridge between different mathematical worlds.
They really are. And then there are higher dimensional categories, which kind of take this idea of morphisms and, they take it to a whole new level. So now instead of just morphisms between objects, we have morphisms between morphisms, and then morphisms between those morphisms, and so on.
Okay. My brain is starting to hurt a little bit again. So what's the point of, adding all these layers of abstraction?
Well, higher dimensional categories let us capture and study these really complex relationships and processes, things that can't be easily represented using traditional math tools. And they're finding applications in fields like topology, multiply theory, even quantum physics.
This is all so mind-blowing. It seems like the deeper we go into category theory, the more connections we find, and then the more potential applications open up.
It is. That's the beauty of it. It's constantly evolving. Category theory, it has these far-reaching implications. It's a real testament to the power of abstract thinking and, how everything's interconnected.
Well, this has definitely been a deep dive, and it's lived up to its name. We've explored all these fundamental concepts in category theory, uncovered these hidden connections between different parts of math, and we even got a glimpse of just how vast the potential of this framework really is.
And the journey doesn't stop here,
Yeah.
right? There's so much more out there to explore in the world of category theory.
Yeah, who knows what incredible connections and insights are waiting for us out there. To everyone listening, keep those minds curious, keep seeking those connections, and keep diving deep.